Find the normal stress at point A in kilonewtons per meter squared. In this problem, a point load of 40 kilonewtons is applied vertically downward at point C to a rectangular prism which measures 0.8 meters long by 0.4 meters wide. The normal stress in the prism equals the normal stress caused by the axial force plus the normal stress caused by the bending moment. If we define a coordinate system whose origin is equally centered between points A, B, C, and D, with the x-axis running along the length of the prism and the y-axis running along the width of the prism, then the 40 kilonewton point load at point C can be represented as a force couple system by translating the point load to the origin of the coordinate system and adding bending moments about the x and y axes to compensate for that translation. Now our equation for the normal stress will need to account for the bending moment in the x direction and the bending moment in the y direction. And the same is true for the distance, y, and the area moment of inertia, I. The axial force term, P, and the area term, A, remain unchanged by the translation. In this equation, the axial force, P, is the 40 kilonewton point load applied vertically downward. And the area, A, is the area of rectangle ABCD, which equals 0.8 meters times 0.4 meters, or 0.32 meters squared. Moving on to the moments, moment X is the equivalent moment which would result from a force of point load P if it were at its original location at point C, times the distance from the x-axis to the location where the point load is applied, y sub x. Plugging in 40 kilonewtons for P and 0.2 meters for y sub x, the equivalent moment about the x-axis equals 8 kilonewton meters. The equivalent moment about the y-axis caused by point load P is calculated the same way, except the distance is between the point load and the y-axis, which we'll call y sub y. Multiplying out 40 kilonewtons and 0.4 meters gives us a value of 16 kilonewton meters. The area moment of inertia terms, I sub x and I sub y, are calculated as the base width multiplied by the height cubed divided by 12. When evaluating I sub x, the base width is 0.8 meters and the height is 0.4 meters. And the area moment of inertia about the x-axis equals 4.27 times 10 to the negative third meters raised to the fourth power. For I sub y, the base width is 0.4 meters and the height is 0.8 meters. And the area moment of inertia about the y-axis equals 1.71 times 10 to the negative 2 meters to the fourth power. In the equation for normal stress, the y sub x term and the y sub y term refer to the distance the point of interest is away from the x and y axes, respectively. Since the equation asks to find the normal stress at point A, we measure out y sub x to equal 0.2 meters and y sub y to equal 0.4 meters. Before computing the normal stress at point A, we must pay special attention to the sign of moment x and moment y. Assuming a positive normal stress represents compression and a negative normal stress represents tension, then moment x will be positive for quadrants B and C and negative for quadrants A and D. Similarly, moment y will be positive for quadrants C and D and negative for quadrants A and B. If we create a table showing the sign of each moment for each quadrant, we notice both moment x and moment y are negative for quadrant A. Therefore, moment x and moment y contribute towards the tensile stress at point A. If we substitute in all 8 variables into the equation for normal stress, the normal stress at point A equals negative 624 kilonewtons per meter squared. When reviewing the possible solutions, the answer is A.